What if I told you that every single law of physics, from the swing of a pendulum to the orbit of planets, from the refraction of light to quantum mechanics itself, can be reduced to one elegant principle? Today we're diving into the most fundamental rule in the universe, the principle of least action. Our story begins in 1696 with a simple question that would revolutionize physics. Johann Bernoulli posed a challenge to the world's greatest mathematicians. If you want to slide a mass from point A to point B, what shape of ramp will get it there fastest? Common sense says take the shortest path, a straight line. But if you bend the ramp down at the beginning, the mass accelerates to higher speed earlier. So even though it travels farther, it might actually arrive faster. The question is, what shape provides the perfect balance? Isaac Newton himself received this challenge in the mail after a long day at the Royal Mint, irritated by being dunned and teased by foreigners. He nonetheless spent the entire night solving it. By 4 a.m., he had his answer, something that took Bernoulli 2 weeks to figure out. Newton submitted his solution anonymously, but Bernoulli recognized his genius immediately. "I know the lion by his claw." But Bernoulli's solution was even more elegant than Newton's. He drew inspiration from an ancient question: how does light travel from one place to another? Hero of Alexandria. Notice that light always takes the shortest path through a single medium. But when light goes from air into water, it bends, it refracts. For 2,600 years, people knew the mathematical rule governing this bending, Snell's law, but no one knew why it worked. Then came Pierre Fermat in 1657. This judge by day, mathematician by night, had a revolutionary insight. Maybe light doesn't minimize distance but time. He showed that Snell's law naturally emerges when light takes the path requiring the least time to travel between 2 points. This was the first time anyone proved that nature follows an optimization principle, that nature does the best possible thing. Bernoulli realized he could use this insight. Instead of a mass sliding down a ramp, he imagined light traveling through layers of increasingly dense media, speeding up as it descended, just like a falling object gaining speed due to gravity. Through this optical analogy, Bernoulli discovered something remarkable. The fastest path isn't a straight line or even a circle, it's a cycloid, the curve traced by a point on the rim of a rolling wheel. This curve has an almost magical property. No matter where you release a mass on this curve, it always reaches the bottom at exactly the same time. Bernoulli wrote triumphantly, "I have solved at one stroke 2 important problems, an optical and a mechanical one, taken from entirely separate fields of mathematics, have the same character." Little did he know he was onto something far bigger. His student, Pierre de Maupertuis, began wondering if light and particles behave similarly. Maybe there's a more fundamental quantity being minimized, something that governs not just light, but all of nature. In the 1740s, Maupertuis proposed action, mass times velocity times distance. His revolutionary claim was that nature minimizes this quantity in all processes. "This action is the true expense of nature," he wrote, "which she manages to make as small as possible." The response was brutal. Maupertuis was attacked, ridiculed, accused of plagiarism. Voltaire wrote a 32-page pamphlet just to mock him. The criticism was partly justified. Maupertuis had essentially pulled his principle from thin air with no rigorous mathematical foundation. But one man believed, Leonhard Euler. This mathematical genius defended Maupertuis and provided the rigorous framework the principle needed. Euler replaced sums with integrals, allowing continuous calculation of action. He discovered that the principle only works when energy is conserved, and identified the precise mathematical conditions required. Then came Joseph Louis Lagrange, a shy 19-year-old prodigy who would complete the revolution. In 1754, he provided the general proof that had eluded everyone else. Lagrange showed that if you want to find the path of least action among infinitely many possibilities, you treat it like finding the minimum of a function. You take the derivative and set it equal to zero. The response was brutal. Maupertuis was attacked, ridiculed, accused of plagiarism. Voltaire wrote a 32-page pamphlet just to mock him. The criticism was partly justified. Maupertuis had essentially pulled his principle from thin air with no rigorous mathematical foundation. But one man believed, Leonhard Euler. This mathematical genius defended Maupertuis and provided the rigorous framework the principle needed. Euler replaced sums with integrals, allowing continuous calculation of action. He discovered that the principle only works when energy is conserved, and identified the precise mathematical conditions required. Then came Joseph Louis Lagrange, a shy 19-year-old prodigy who would complete the revolution. In 1754, he provided the general proof that had eluded everyone else. Lagrange showed that if you want to find the path of least action among infinitely many possibilities, you treat it like finding the minimum of a function. You take the derivative and set it equal to zero. This single principle unifies everything we once thought were separate phenomena. Light refracting through water, planets orbiting the sun, pendulums swinging, particles colliding, all are manifestations of the same fundamental rule: nature optimizes action. But the story doesn't end with classical mechanics. At the dawn of the 20th century, action became central to solving the UV catastrophe, launching quantum theory. Today, the principle of least action underlies quantum field theory, general relativity, and our deepest understanding of the universe itself. What started as a simple problem about sliding masses, down ramps revealed that all of physics emerges from a single, elegant optimization principle. Nature, it seems, is fundamentally economical, always finding the most efficient path through the landscape of possibilities. The principle of least action stands as perhaps the most beautiful and unifying concept in all of physics, proof that beneath the apparent complexity of the universe lies profound simplicity.